Welcome to track 5, Palace 3 for Out of Control Demonstrating SCADA Device Exploitation with Brian Meixel and Eric Forner from Cimation out of Houston. And I'll turn it over to them.
Okay, so on our agenda today, we are going to be going really fast through basic SCADA 101 because I think a lot of people already have seen some SCADA talks and know the components around SCADA systems. We're going to talk through about 3 scenarios that an attacker could do on this system that we built to simulate a process, and we'll mention that in a minute. We'll discuss some common vulnerabilities that we've seen in different SCADA devices and other industrial equipment. We'll also go over some remediation security controls that can be put into place to prevent some of those attacks and go through the demo here.
Yeah, so I guess if we want to just go quickly over what we have here. So if any of you have ever seen one of these before, this is a controller. Maybe I can actually get down quickly. So this is a control panel. So you see these all over the place in well pads. You see them on offshore oil platforms. This is what actually controls the process. This controls the field instrumentation. So this is actually a control panel that's used in production. So usually what we do is we install these things in oil wells all the time. But of course we couldn't bring an entire oil well here. So what we made was this simulated oil well. So just to kind of give you a brief overview of what we have is we have a simulated a well itself. It goes up to a pump, then over into an isolation valve, and then up into our simulated tank. One thing that we also have here is this little brass guy, and what he's a pressure safety valve. So you see those a lot in industry to prevent overpressures, but sometimes in production, you'll have this pump, an isolation valve with no PSV in between it. But we had to put one in just because we don't want to spray water everywhere. So we put one in for that. One other thing that we have up top is this little screen right here. That screen is called an HMI, and that's kind of the visualization of the process. And we can give you a quick show of what it looks like to actually work. So all this stuff is touchscreen, and you usually see these installed in the field.
The HMI is the operator's view into the process, and it also allows some control. And you typically see alarms pop up if you have any conditions that are met on the HMI.
Exactly. So what we're going to show is just how the system is supposed to work, right? So the way that we've designed this and the logic that's actually in the controller itself, we turn on the pump, we make sure that this isolation valve is open, because if it's not, we end up overpressuring right here. And we also make sure that when our pump gets to 100, we call it level 100, but it's about 3 inches below the top, we shut off the pump as well. So these are intrinsic safeties that are inside of this controller itself. So we can quickly demonstrate. We go through, and we're starting to pump, and our level is starting to go up. But what we'll end up seeing is I'll end up from the human-machine interface shutting off this valve, and then the pump turns off. So this is all implemented in logic inside of here. And we can show a little bit later what happens when we raise the level of the tank itself.
Yeah, it's just going to automatically shut off the pump once the level is reached to be full.
Okay, so when we talk about a control system, we have this small guy right here, and this is just a controller with some field instrumentation and an HMI. But there's a lot more to it. So what we have here is we have just a kind of top-down model of what a real control system looks like. So if we start from the very bottom, we see our field instrumentation right here. So this is your field instrumentation. This field instrumentation is controlled controlled by the controller itself. The controllers, or the PLCs as we call them, communicate with each other over this control bus, and we go up to the HMI, which is right here, and then we go on the plant bus, and that's kind of where the plant LAN is right there. And then we go up to the enterprise, because the enterprise needs to get all this data from the control system for enterprise resource planning and all types of different things. When we talk about a DCS network, if you've never heard of DCS, it's a distributed control system. And usually we have that control bus, but that control bus needs to be very real time, and it's usually all part of a plant LAN, essentially.
So DCS is usually used in factories or automation, all contained within one location.
Exactly. It's when you require real-time data. SCADA is a little bit different. So when we look at SCADA, a lot of the architecture is the same, right? But what the main differences are those gray guys down at the bottom. And those gray guys show us that usually these PLCs are geographically spread out, and there's all different types of mediums that you use to connect that PLC up to the terminal bus is what they call it. So that's how you get that data from the PLCs out in the field to the HMIs back at the control center. So we kind of showed some graphics here, but it can be anything from 900 megahertz radio, it can be microwave links, and it can be, of course, our favorite, a regular old cell modem that's given a public IP address. There we go.
Yeah, and this is a typical SCADA network. This is kind of the recommended network architecture where we have multiple firewalls in place to segregate the traffic types. However, if we move on to our next portion here, most firewalls, a lot of the firewalls that are implemented are really just put in place because somebody needs to comply to a standard, and they end up leaving their firewall just allowing all traffic to pass, which isn't really a firewall at all.
That's right. So essentially what we see is we see routers, right, in this control system. So yeah, for compliance sake, they always have these firewalls in there, but all those firewalls are any, and we see this in the field a lot. So they design the segregation in there, but in reality, it's just a routed network, just like anything else.
And even worse is no routers at all, or no firewalls, where everything is on a flat network and everything can talk to anything else on the network.
Yeah, anything from your SAP up to your web server can talk directly and is on the same LAN. So just broadcasting, it'll be on the same LAN as your actual PLCs and your controller hardware.
And just briefly, we're going to go through and point out some of the components that we do have here. Historian is not represented in our demo, but the HMI is the panel you see up there that's displaying a view. That's just how like I said, the processor or the operator views the process and has some control. The application server is really just any computer that aggregates the data from the field to bring up to the network. An engineering workstation allows an engineer to modify the logic on a controller and really build the process. So this machine is really kind of the key to uploading or changing logic for the process. The PLC is, do you want to point that out?
Yeah, sure. So the PLC, they're called PLCs, controllers, or RTUs, remote terminal unit, but it's this guy right here. He's what actually controls the process.
So a PLC takes inputs such as a temperature sensor, or in our case, a level sensor, and has logic that it acts on those inputs and writes outputs to the system, which controls a pump or a motor or a valve, things like that. An RTU is very similar to a PLC. Might have some more capabilities and more logic available. So instrumentation is in our demo just the pump, the valve, and the level sensor here. That's kind of sensors and devices you're controlling in the field. All right.
Right. Okay. So when we want to talk about actually getting into this network, well, there's a couple of different ways, but normally what you would see if you were doing a traditional pen test is your most exposed network would be your enterprise network. And we'll kind of go down sort of quickly about how this goes down, but there's a lot of data flow that comes down from that R2 all the way up to your enterprise network. So if your enterprise network is the most vulnerable, or at least has the most exposure to the internet, we kind of have to pivot down through there. So we can kind of go through some of the main components involved. So first, we go from our enterprise resource planning server. So that's how we get orders and all types of different stuff down from the control system. But if we go from that ERP server down to a historian, well, what does a historian do? Well, a historian takes information, the information from the RTU and stores it, and it has to be stored for a certain amount of time for environmental compliance and all types of different things. It's typically a Windows Server class machine, but if you end up owning that, you are able to modify the worldview of the process to the corporation and to the government. So one main thing that you think about is when you go after a historian is you would be able to modify different points that are of interest to environmental agencies such as like NOx flared or something like that. So even though you're not down on this control system, and we don't even have a historian here, you can cause real damage by getting inside of a historian.
You're talking about ruining a company's reputation, ruining their shareholder or their stock price, and possibly getting multiple millions of dollars of fines from regulation violations, that sort of thing.
Cool. So a historian usually gets data from somewhere, right? It has to get that data from the plant bus or the terminal bus. And so usually it draws that data from any number of sources, but we're going to say it gets it from the HMI, because the HMI stores that data real time, but it doesn't have enough capacity to store data for years and years like a historian is required to do. So when we go from a historian down to an HMI, we have a bunch of different communication paths. One would be just regular old historical data, but what we're going to mention quickly here is OPC. If any of you have heard of OPC, it stands for OLE for process control, or object linking embedding for OLE. Essentially what it is it rides on top of DCOM, which many of you might know is a deprecated protocol used by Microsoft, but it's used everywhere in the process control industry. And the implications of that is that because it uses DCOM, you have to open up a ton of firewall ports, or a ton of ports on your firewall to allow that data to traverse it, because it picks a port at random to assign to that OPC communication. So even though it's deprecated by Microsoft, you see it everywhere in the process control industry. So we got to an HMI, and like Brian said, that HMI is this guy, and he's the operator's view of the world. The HMI does not control the process. All it does is provide a visualization and allows the operator to request changes on the controller itself. So if we're on the HMI, what we're able to do is actually spoof the process to the operator, maybe not modify the process itself, but modify the world view of the process to the operator. So one thing that you kind of can see here on this diagram is that there are two HMIs, and that's typical in a process control network. So if you end up getting on an HMI, you have to be very careful to synchronize that modification across all HMIs, unless you get to what's called an application server. So if we get to an application server is essentially a data aggregator from the controllers, and that's important because these controllers are not very powerful devices at all. All they're supposed to do is scan their logic, scan their inputs and scan their outputs, and control the process. They're not meant to be getting a lot of polls from all of these HMIs that might need information from it. So you have this application server that pulls data from the controllers and then filters that data up to the HMIs. One thing that's nice about that is if you're able to get onto that, you're able to modify that worldview of every HMI that talks to it. So now, once we get through the application server, we're actually on the control bus itself. And the control bus is what actually has the PLCs communicate with each other, and then we get to an engineering workstation, what Brian was talking about. And what the engineering workstation can do is actually modify logic on the controllers itself. So that picture up there is of an engineering workstation program, and we'll talk about this a little bit later, but the language that you write on these PLCs is not C or anything like that. It has a couple of different forms, but primarily what you'll see is what is called ladder logic. And you can see obviously why it's called that, but it's essentially an old programming language that's relay logic. So it's meant for electrical engineers, not so much programmers. But what you can do is if you're on an engineering workstation, you can actually steal the source from the controllers themselves. So you can actually get the logic files and modify the logic files on the PLCs while they're still online. And why that's important is because in the olden days, you had to take a PLC offline, modify the logic, and then bring them back up. But you don't have to do that anymore. And the reason that you don't have to do that anymore is because plants require almost no downtime. You need your wellhead to be up all the time. So you're able to modify logic real time without ever bringing down the process, which is awesome for a hacker, right? Because nobody actually knows that any change has ever been made. The process keeps going on normally, or how you want it to go, but you never have to actually take it down. So we're on the PLC, and then the PLC is actually what controls the process. So once you're there, and this is what we'll be demonstrating, you have complete control of your process, because this drives the outputs in your actual process. So we're on a PLC, and a lot of you probably know what a PLC is, but we'll just go over it quickly. It's usually just an embedded piece of hardware. It runs VxWorks or some BusyBox distro or some old crusty RTOS, QNX or something like that. And some of them, God forbid, write their own operating systems. But once you're on there, you can actually write arbitrary memory. And we'll talk about what the input table and the output table are in a little bit, but those are extremely important parts of the controller itself, because that's what actually drives these I/O cards and the instrumentation that's attached to it. So we think that it might actually be kind of hard to get to one of these PLCs or to an HMI. But the thing is that it's actually pretty easy, because a lot of these HMIs and engineering workstations are Windows-based machines, and they're woefully out of date. And the reason for that is because in production, you never want production to go down, right? Because you want these things on for 20 years or so, and every day that you're not producing oil or every day that you're not producing some chemical is money down the drain. So you want to keep them on all the time and not necessarily updated. And also vendors have to approve all patches. There's all types of complications that come with having a computer that's part of the process control network as opposed to being on regular old enterprise IT. But we were talking about all this pivoting and all this nonsense, but in a SCADA system, it usually doesn't matter, right? Because a lot of times, something like this, you have an Ethernet cable coming out to some wireless cell modem, and it's just hooked up to the Verizon network with a public IP address. So, I mean, what could possibly go wrong, right? So we don't have to go through the enterprise network and make our way down. We just go right to the controllers itself, and that's what we're going to show. Okay, so there's a couple of different things that we can do with the controller. One thing is that we can actually do binary exploitation of it, traditional buffer overflows and stuff like that, because a lot of these guys don't have the protections that you would see in a normal Windows machine, such as DEP and ASLR. These are just really old, simple machines. But what we want to do is we want to actually go after the protocol itself. We actually want to build a packet to tell the controller to drive its I/O without actually modifying the logic, just telling the logic to essentially be quiet and drive those signals ourselves. So we'll talk a little bit about industrial protocols. So we have a couple of them. The one that we find most important is this Modbus TCP protocol. It's TCP port 502, and it's been around since the 1970s in serial form. So what they ended up doing was taking this Modbus serial datagram, wrapping it in an IP frame, and saying now we have things that can be networked, right? But the problem with that is, of course, is that no encryption or no authentication or any sort of security concepts at all were ever designed into this. So we can sort of take advantage of that. And that's what this guy speaks right here. So we have a couple other protocols that are open and are used pretty widely. Ethernet IP is one, Profinet is one. But we, like I said, there's an obvious reason why we chose TCP, and it's up there, because there are 93,000 nodes on the internet from the Internet Census of 2012 that are listening on TCP port 502. It may not necessarily be an RTU or a PLC. It might be one of these guys, but Modbus is used to control processes out in the field. So at the end of the day, what we want to do is we want to construct a Modbus datagram. And when we construct that Modbus datagram, what we want to do is we want to send a signal out to this PLC to drive outputs regardless of whether or not there's safety logic involved. So I'm sure everybody's seen this before. This is a regular old TCP datagram, but what we're going to do is we're going to do Modbus, which is TCP port 502, and we're going to add our own Modbus data in here to drive this process. So we want to construct a Modbus datagram. So how do we do that? Well, the Modbus datagram is actually extremely easy. It's extremely simple. First, we have the very first byte, our transaction ID, and the reason why that's kind of cool is because that's actually a legacy of an older serial protocol, because you don't need this transaction ID anymore, right? Because that's handled by higher level or higher layer protocols, but they still have it in there to maintain compatibility with the older devices. A protocol ID is always 0. It's always 2 bytes of zeros, no matter what. And you have a simple length counter, a unit ID, also a holdback from the serial days because it's always FF. No matter what, because in the old days you would address it with a unit ID on a serial line. You don't do that anymore. It's addressed by its IP address, but it's still in there. And we have a function code. These function codes we'll go over pretty quickly because these function codes are what actually drive signals in the field. These function codes, such as function code 1 is read coil. Well, what's a coil? A coil is a digital output, just a 1 or a 0, something that drives something in the field. And we can also we can read a discrete input, so a 1 or a 0 as far as a prover to say whether or not this is open or closed. We can also have other function codes, like it's a holding register and an input register. And all a register is just either 16 or 32 bits of data that is used to hold an analog input or an analog output. So something that can't just be represented by a binary, something that's a little bit more, such as one of these guys, this level sensor would be an analog input. So we would call that a holding input register. So if we want to just turn on a pump, we can do this pretty easily, right? All we have to do is design or just construct a packet to tell it to turn on. So we just give it whatever transaction ID we want. Protocol ID is always 0. We just put in a length counter, and then we give it a function code of 5. That function code of 5 is write coil. So write, drive a coil, write an output. And then we give our data. So our data is that's that table down there. So we have our most significant byte of our reference number, our least significant bytes of our reference number, and I'll tell you in a sec what a reference number is. Whether or not we want it to be on or off, FF is 1, 0, 0 is off, and the last one is just always 0. So we have this word of caution down here, because Modbus is a really, really ancient protocol. There's not really a way to know what you're driving. All you know is the reference number. So unless you get on an engineering workstation and you find that reference number mapping that maps just a reference number to a physical piece of equipment, you don't know what you're actually driving. But sometimes you just don't care, right? So sometimes the reference number is in a very specific part of addressable memory. So what you can do is just do the nuke option, just turn them all on. And we can do that, and we will do that, and see what happens. But alas, there are some complications with doing that. So control engineers like myself would implement safety logic in there to make sure that an operator or hopefully a malicious entity, whether they're driving an output, the logic inside of the controller would stop bad things from happening.
Do you want to demonstrate the interlock, safety interlock there, where you can try to close the valve while the pump is running?
Sure. So yeah, so we have our pump on, our valve is open, so everything's good, just like we showed before. And when we turn it off, our pump turns off. And we'll also show you here. While this thing's running, this thing will keep on pumping up until we hit 100. Sorry, you might get sprayed a little bit. But we design that logic looks like these ladder logic diagrams up here. So we call them interlocks and permissives. An interlock prevents two states from happening that shouldn't be happening at the same time, such as we don't want to send current to our forward coil and a reverse coil of our motor because it'll end up shorting it out. So we implement logic in there. All right, it just went off. Cool. Logic works. We end up putting in that logic to say you can't hit the forward and reverse button at the same time and cause a short.
Or another example might be you can't have all the lights in an intersection green at the same time. So there's a safety logic built into your intersection.
Exactly, exactly. So that sort of stuff is implemented in the logic of the controller itself. And we also have permissives, and that's what we did here is permissives. So we will only allow activation of our pump if this guy is open. But what we can do is if we have access to the PLC or if we have access to an engineering workstation is just remove it. So even if you don't have, let's say that you're not on an engineering workstation, you don't have the source, you can still get we could call it the disassembly from the controller itself. And that's what we're looking at up top there on the top right. So we can pull that from the PLC without ever seeing any source code. And that's what it looks like up there. So all you know is input 0 or output 0. You don't know what's actual its mapping is, but you can kind of see the control flow of how the controller is supposed to look. So even you don't have to be on a Windows workstation to actually get a baseline of what is actually happening on this controller itself. But if you do, which we have down there in the bottom right, what you can do is remove that safety logic. So over there on the very left-hand side, all we did was remove that overload. We don't care anymore. You can overload it, and the safety logic will not prevent anything from happening because we just remove that safety logic, re-download, they call it download to PLCs, I don't know why, but they do. You download that new logic to the PLC while online, and your safety logic is gone. Your process still runs normally, but there are critical safety features that are no longer present in logic. So when we talk about spoofing, so we can go back to regular old Windows or PC-based exploitation and just do regular old send-receive hooking if we don't care about modifying the controller itself. So what we can do is if we're on this controller, we can go and hook the packets, the Modbus packets that are coming back from the PLC and modify that world view to the operator and everyone upstream, the historian, the ERP, everything else, without ever getting to the controller. But it's also preferable to hook an application server. And the obvious reason for that is because you can have any number of HMIs, but you usually have one or one-in-one redundant application server that's kind of that funnel that goes between your process, your actual process, and the higher levels. But one thing that's kind of cool, and one thing that you can do is actually exploit the Ethernet card on these controllers themselves, because these Ethernet cards are afterthoughts when it came to PLC manufacturers, because usually this talks serial, so they just develop a plug-in device. This one is not an example, this one's actually plugs into the CPU itself, but a lot of times you'll see an Ethernet card, and this Ethernet card plugs into the backplane of the PLC, and this Ethernet card just runs some old version of Linux because they didn't feel like writing their own TCP stack. And it just never, ever, ever gets updated. So you don't even have to do a binary exploitation of the PLC that might be a little bit hardened or very weird and obfuscated. All you have to do is go after some really old, operating system that's running on the Ethernet card itself, and you are able to spoof all of the transactions from the PLC all the way up.
Yeah, so some of these common vulnerabilities we've seen in several different devices we've looked at involve direct memory access, where we can use a debug process that is actually often left on the devices by the manufacturer for troubleshooting or service purposes, and you can manipulate the entire memory space to control anything you want.
Right, so when we talk about what a PLC does, right, so a PLC does very, very simple things. First, what it does is it scans inputs, all of the inputs in here. So it scans the state of this, and then it writes it into what they call an input table. That input table is just a memory region where it keeps the state of all of the inputs that it gets. Then there's a logic memory region, and that's just where that executing ladder logic process is. And then we have an output table. The output table is what actually drives the I/O cards that are on that controller itself. So all a PLC does is scan inputs, write those states into its input table, performs logic on those inputs, and then writes outputs, sends those outputs to the output cards, and then actually sends signals, physical, electrical signals out to your instrumentation, and it does it over and over and over again. It does little else than that.
So quickly, I'll talk about some remediation. A lot of the security on network security is similar to the enterprise side. Making sure your architecture is compliant and your standard architecture with firewalls, and trying not to have a public IP for some field devices that anybody could just talk to. Your host level antivirus is old and antiquated, but it's still the best practice, so it's still used a lot. At the host level, control systems are especially well suited for newer technologies like application whitelisting, because they only really do a few things and they're not used for general purposes. So they'll restrict the programs that can be run on those endpoints. At the device level, a lot of the device level remediation is up to the vendors and the manufacturers, but there are devices you can put in front of your controllers, kind of like a device level firewall that will filter commands that the device can get to. All right.
Now we get to the fun part.
Yeah.
So just to kind of give you guys another brief overview of what we're looking at here is we're looking at a simulated wellhead process. And so this is just a little 24-volt pump. This is just a tiny little 24-volt solenoid valve. But it doesn't matter, right? Because this PLC right here sends signals out to the field. And this could be a 24-volt pump or a 10,000 horsepower motor. It doesn't matter. It's just a signal. It just matters of what we could actually fit in our car and drive here with. But anyway, so what we're able to do is, just go over to the next slide quickly, is we're able to actually do catastrophic failure on this. So one of the things that we were talking about is that we have safety interlocks and permissives on here that do not allow this pump to turn on if this valve is off. Well, it doesn't matter what the safety logic has. If you drive these output signals directly, you could be sending logic to turn off this pump all day. But if we actually drive the signals itself in this PLC, it doesn't matter what the operator wants to do. It doesn't matter what the PLC logic wants to do. We're driving those outputs ourselves, and we'll get to see that.
Yeah, let's do that.
Okay. So we just got a couple of quick and dirty Python scripts here. Except for us all. Hope we don't get cursed to the demo.
So right now, all the inputs are forced to high.
Yeah. And we're just sending Modbus packets. That's all we're doing. Is we're just asking the PLC to do what we want it to do and ignore logic. So in real life, let me turn it off quickly. So in real life, that would be a pipe blowout. Yeah, this is just a safety valve here, but in real life, that could be oil or acid or anything that could be in, we live in Houston, it could be in our backyard, could cause complete environmental catastrophe by just doing something that simple. It's not rocket science, but it's extremely dangerous. So there's one other thing that we want to show. Want to give the
yeah, we're going to show how we can keep running the pump while the level sensor is already reporting that the tank is full and cause a tank overflow condition. But at the same time, if you look at this panel, we'll be spoofing data to the operator to show that the tank is actually decreasing, so that, you know, a lot of operators think the worst thing that can happen is they lose visibility into their process. But what really the worst thing that could happen is their a data incongruity there, so they don't really see what's actually going on.
Okay, so we'll give it a shot. We'll see what happens. So what we're doing is we're actually iterating through every Modbus. That's why it's taking a little bit, but it's iterating through every Modbus point and just turning them all on. Okay? But what we want to do is we actually want to tell the PLC what to think. And we can do that. Right, let me give you a better view here. we're actually showing that the PLC, or we're showing on the operator screen end of the PLC that the tank is actually decreasing. So even an operator would not even know, even if he heard that this pump was on, because these things are never clear, right? He would just keep the pump going on because he sees his level actually decreasing. And this can be arbitrary. We just have it decreasing slowly as an example. But in reality, anything can happen. So, I mean, I'm not really sure what's going to keep happening here, but I can probably tell you that this pump is going to keep on going because he thinks that level is decreasing. And the Black Hat people told us not to make it overflow, but whatever. Have to hit E-stop. You can't do anything else. You have to, even if you push start or stop on that HMI, it wouldn't matter. You have to cut the power.
So because the operator saw something different than reality, he might take a different course of action and cause even more destruction.
Right. So, I mean, this just kind of shows how easy it can be to force the outputs of a process. And this is not binary exploitation. This is just telling the PLC what points to turn on and off and what its worldview of the process is, and tell it to disable its own logic scanning. So it just, all it does is what it's told to do. And the operator always makes control decisions based on what the PLC is giving it. So if we go directly to the PLC, and we went after these because these are in remote well sites that don't have easy access to regular old LAN, so you have to have some sort of connectivity back to your corporate office, and a lot of times it's cell modems. So these are publicly addressable on the internet. So, I mean, something has to be done about this, right? I mean, it's almost trivially easy, and you can see what can happen. I mean, this is just a demo, but this is for real. So, thanks for coming.
All right. Do you want to show the last scenario?
Yeah, one more thing. So, just one more thing. So we were going after the PLC the entire time. But, you know, we were messing around a couple of days ago, and we're like, well, what can we do with this crazy little HMI? And we were getting a little bit bored. And let's see what happens here. This might go down for a sec, but we might be able to upload arbitrary binaries and execute them on the HMI as well. So we'll see what happens there. I'm like, it's touchscreen too, so that's what you can do. Just want to have a little bit of fun.
Thanks.